Okay, good morning, everyone. Let's continue our discussion of AC analysis. Let's see, where did we stop? Let me bring up. Oh, that's not the right one. Right here. Oh, yeah. Yes. Yes. Well, it depends on who's teaching it. It's same format as this one. 40%, 30% plus 10% homework, 40% quizzes, and 20% final exam. Same book. I'm the only one who uses a different book for 321. I'm teaching it this quarter, but I'm on leave next quarter, so I'm not scheduled to teach 321 next quarter. Fall, that's the hope. Yeah, so anyway, let's continue with this and we can talk about all of that after class ends. So our discussion was that when you have an AC source in a circuit and you have RLC components, the resistor R behaves exactly the same way that it does for DC. So there's no change in that analysis. Whereas for an inductor and a capacitor, it is different because the voltage and current are time dependent, right? They vary, the voltage and current values vary with respect to time. We have to solve differential equations. So to make the math a little easier, make the math a little less complex, we use complex numbers. So the sources are represented as a vector quantity that is rotating counterclockwise in the complex plane. And it needs only two things to describe it, which is basically the length of the vector and the angle it makes with the real axis. Let's go to the right one, section 1. It's right here. Okay. And so it needs only two things. The length of the vector is defined or given by the magnitude or the peak value of the waveform. What's going on with my pen? There we go. The vector is described as Vm with a phase angle theta. And from the time varying expression V of t, the length of the vector is given by the peak value or the magnitude of the waveform, and the angle is given by the phase of that waveform. And hence the reason why we describe those quantities as separate, right? One thing that students have to keep in mind is that the expression has to be in cosine format. Okay, so if the expression is given to you in sine, then you have to use this trigonometric identity. Sine x is equal to cos of x minus 90. Simply stated, if this was sine omega t, you simply subtract 90 degrees from the phase. If the phase was 0, so if it was sine omega t, then it would become cos omega t minus 90. Right? You just subtract 90 degrees from the phase, and you would get the right, phase angle. Then you simply take the magnitude from the expression and the phase angle, and draw out your vector, or describe your vector. Okay. So that was for the source. Let's talk about inductors and capacitors. So inductors and capacitors have what we call as reactance. Okay, reactance. Reactance is a quantity that is associated with the stored energy in the magnetic field and the electric field for the inductor and the capacitor respectively. Okay, reactance. And that is noted by the letter X, uppercase X. So what is, well, to just describe it in brief, reactance has to, all three quantities here have to do with opposition to something, right? It's opposition. Resistance is the opposition to the flow of current. Reactance is the opposition to the change in the incoming input, okay? So in an inductor, for example, we have an incoming current as input. The energy is stored in the magnetic field, and that gives rise to a voltage in that magnetic field. It's known as the back EMF because it opposes, the voltage polarity opposes any change in the current that is initially flowing through that inductor, right? As long as the current is constant, it behaves like a short circuit. But the moment you try to change that current, it's going to oppose any change in that current. And the faster the change, the more the opposition. And that simple statement is going to be very important for our calculations. Because the faster the current changes, the higher the opposition from that inductor. So that is reactance. And the same thing for the capacitor. Capacitor stores energy. You have voltage across the capacitor. When you try to change the voltage across the capacitor, it opposes any change in that voltage. Both of those oppositions are described by the term reactance, X. Now, resistance, pure resistance, up till now, we have only dealt with in a pure resistor. So a resistor only has resistance. It does not have any reactance. Again, it has to do with energy storage. A resistor cannot store energy, so a resistor does not have any reactance. And we represent resistance and reactance using complex numbers. Resistance is the real part, and reactance is the imaginary part. Emphasis on that reactance is not imaginary. It is imaginary only in mathematical terms. Okay? So you'll often read or hear the statement saying that, oh, reactance is imaginary. Okay, so what they're referring to is reactance is mathematically imaginary because it's represented by the imaginary number J or I in your own fields, if you will. And then this entire sum is represented by a term known as impedance, noted by the letter uppercase Z. So Z is equal to R plus JX. That's where it comes from, okay, impedance. All three quantities describe opposition. So the units for all three, ohms. Okay, units for all three are ohms. A resistor does not have any reactance. So impedance for a resistor is R plus J0. And hence it is just ZR is equal to R. Effectively, there is no such thing as impedance of a resistor. It is simply the resistor R itself. Okay. So in AC analysis, when we say, oh, we have to analyze the circuit, and if there's a resistor in there, you simply, when you convert it to the equivalent impedance circuit diagram, we simply put R as it is. There's no other change to that value. So ZR, again, there is no such thing as ZR. I just put it on there as a, for explanation purposes. Impedance of a resistor, if we use this exact equation, R plus JX is simply R plus J0, so it's simply R. Ideal inductors and ideal capacitors do not have any resistance. So it's R plus JXL. The subscript L simply refers to inductor. So the impedance of an inductor is simply JXL or JX. Same thing with a capacitor. Capacitor is simply 0 plus 1 over J XC, or actually 1 over J XC. There is an explanation for why it comes out to be 1 over J and positive for the inductor. Okay, it has to do with the differences in phase for the inductor and the capacitor. I'll talk about that in just in the next slide. But does this make sense for now? Right? ZR, impedance of R is simply R. ZL is JXL. ZC is J1 over JXC. Okay. Now, oh, sorry. what happens is, and there is a small derivation which I typically don't do in these classes, in 2-1 classes, but when you apply a current or a voltage to an inductor or capacitor, energy is being transferred, right? Energy is being transferred. That energy transfer takes a certain amount of time. We learned about that in chapters 3 and 4, transients. And so what happens is that there is a phase delay between the voltage and current for both inductor and capacitor. So there is a phase delay, and that phase delay comes out to be, for a inductor, the inductor voltage is ahead of the current, or the inductor current. And for the capacitor, the current is ahead of the voltage. When I say current and voltage, I'm referring to that specific component, meaning the voltage for that inductor is ahead of the voltage for that capacitor. Remember, ahead, behind, leading, lagging, right? So there's a difference in phase. So basically the arrival points in time of the peak values is different. Actually didn't do an audio test, but I assume everyone can hear me.
Yeah, I can hear you.
All right, thank you. So voltage is ahead of the current for a inductor. For a capacitor, the capacitor current is ahead of the capacitor voltage. And in both cases, the difference in phase for both. So when we say ahead or behind or leading or lagging, you're talking about phase difference. Any guesses? Of 90 degrees. So theta is 90 degrees. Okay, so the phase difference between VL and IL is 90 degrees. So if I was to expand on that, I would say phase for the inductor voltage minus phase of the inductor current is going to be plus 90 degrees. And the phase for the capacitor voltage minus the phase for the capacitor current IC is going to be minus 90. Minus 90. And hence we represent it with 1/J. Any questions so far? So again, last class and this class, there's going to be a lot of concepts coming at you. So feel free to interrupt at any point. There's a mnemonic that we use, or at least that's what I use to help me remember. Eli the Iceman. Eli Manning invented it. It's named after him because he's got ice in his veins. Not really. I don't know where the origin comes from, but let's take a look at that phrase. You know what L stands for? You know what C stands for? You know what I stands for? What is E? Electromotive force, voltage. So in an inductor L, the inductor L, the voltage comes before I, right? The voltage is before I. And in a capacitor, the current is before the voltage. So in an inductor, the voltage leads the current by 90 degrees. In a capacitor, the current leads the voltage by 90 degrees. Eli the Iceman. Okay. It still helps me to this day. If I have to think on the spot in like 2 seconds, it's like, well, okay, what? I think of that phrase and it helps me. Okay, so why are we doing phase of voltage minus phase of current? Why not the other way around? Why not the other way around? Well, it has to do with the equation for the impedance. Impedance uses the exact same equations that we use for Ohm's law. Okay, so if I was to find the impedance for a resistor, inductor, or capacitor, I can apply Ohm's law. Actually, it's in one of the slides in just, it's right there. So V is equal to I times Z. Okay, so Z is V over I. So ZL is VL divided by IL, and ZC is VC divided by IC. Okay, and then I will get into the maths. So the equations that we learned about in chapters 1 and 2, they would apply in the exact same manner. If you wanted to find the voltage for an inductor or a capacitor in chapter 3, remember what we did. We had to take the derivative or we had to take the integral. Now we simply use complex maths and apply Ohm's law. So no more differential equations to solve, no more derivatives to take, no more integrals to find. And that's why we say, or at least I say, that the maths is now less complex because of the use of complex numbers. Okay. All right, questions? Any questions at all? So then let's go back here. I'll talk about those equations in just a bit, but let's talk about the vector. So impedance, again, as I said, R plus JX. R is the real part, X is the imaginary part. And if we plot that in the complex plane, we can find a vector, we can write a vector with a length of R and a phase angle of theta. Right? So the real part A, imaginary part B, is related to the vector by A plus or minus JB as magnitude R and phase angle theta for the vector. The magnitude and phase are known as the polar coordinates, and these are the rectangular coordinates, right? Rectangular coordinates. So when you have Z is equal to R plus JX, when you have Z is equal to R plus JX, you can write it as magnitude of Z with a phase angle theta. Now, as engineers, you would have used complex numbers in your own field. If you have not yet done so, you probably will encounter, some techniques where you would have to deal with complex numbers. So it's the exact same thing that we're using here. Polar coordinates, rectangular coordinates. And when you perform maths in polar and rectangular coordinates, it is easier to perform addition and subtraction in rectangular coordinates and multiplication and division in polar coordinates. Now, modern scientific calculators or engineering calculators can perform any operation using any coordinates. I mean, even manually, we can perform that math easily. I mean, not easily. We can perform the math in any coordinate we want, all four mathematical operations. But it is easier if we do this addition and subtraction in rectangular and multiplication and division in polar. Okay. Now, my calculator is from the 90s. So it is an engineering scientific calculator. It was not programmable. At the time, we were not allowed to have those. And so it can only perform certain specific calculations. The modern calculators that you use, most of you, I'm guessing, have the Texas Instruments model, like 83, TI 83, 84, 84 plus. And those you can perform, you can just take an entire equation, program it in there, and it spits out a final answer, right? And when we solve problems, you will see what I mean. But I have to actually do these conversions. which is also what the textbook shows. Okay. Does this make sense so far? So if you think of Z, we come back here. From Ohm's law, I can write Z is equal to VI. So ZL, oh, sorry, not Z is equal to VI, Z is equal to V over I. So ZL, what is ZL? It is VL divided by IL, and ZC is VC divided by IC. And when you perform division of two complex numbers, what happens? Any guesses? So this would be magnitude of Z with a phase angle of Z is given by magnitude of V, theta V, divided by magnitude of I with phase of I. Any guesses on how this operation is performed? So if you're dividing two complex numbers, the magnitude gets divided. That means no one has completed the complex number sheet review on Canvas.
You subtract the angles?
Phase angles, absolutely. You subtract the phase angles. And hence, for the impedance of an inductor and a capacitor, we do theta V minus theta I. And because the inductor voltage is ahead, you get plus 90. And because the capacitor current is behind, I'm sorry, capacitor voltage is behind its current, we get minus 90. And hence 1 over J for a capacitor impedance and plus J for an inductor impedance. For multiplication, you multiply the magnitudes together and you add the phase angles. Addition and subtraction is, of course, you add or subtract the real parts together, add or subtract the imaginary parts together. Okay, questions? Does it all make sense? Why? I mean, there are mathematical derivations where you can prove, we apply sine x or cos x to an inductor or capacitor, and we can actually prove how and why it comes out to be plus 90 and minus 90. Okay, but I typically don't do those for 201. So the other equations, the equations that you've seen here and what I haven't talked about yet so far. What did I say? When you have current going to the inductor, it gives rise to a back EMF. It opposes any change in that incoming current. So if the current starts to change a bit, right, there's opposition from the inductor. That opposition is defined as the reactance, or in totality, it's impedance. So impedance of an inductor. Change, if it changes slowly, the opposition is lower. If it changes faster, the opposition goes higher. So think about the change. What does it mean in technical terms? One cycle in 1 second. If it's now 10 cycles in 1 second, what are we doing? We are increasing the frequency of the incoming signal. So the faster the change of the incoming input signal, the higher the frequency, and the higher the frequency, the higher the impedance. And hence the equation ZL is J omega L. Omega is 2 pi F. Omega is 2 pi F. So ZL can also be written as J 2 pi FL. The inductor impedance is directly proportional to the input frequency F. As F increases, the opposition increases, inductor impedance increases. So at very, very low frequencies, inductor behaves like a short circuit. Going back to chapter 3, when F is equal to 0, inductor impedance is 0 because F is 0 for constant DC voltage. Comes back full circle. right? So this also works when you say we are applying a DC voltage. So DC current or DC voltage, F is 0, inner impedance is 0. Capacitor is just the opposite, right? Capacitor, you apply a DC voltage, meaning it's constant, it reaches full charge. Once it reaches full charge at steady state, it behaves like an open circuit. But now if you decide to change the voltage across that capacitor, electrons will start moving again in that circuit, right? Back and forth. So slow change, again, slightly higher opposition. The faster it changes, the more current flows into the circuit, meaning the opposition from the capacitor is actually low. So capacitor impedance behaves exactly the opposite. And hence you get this equation. ZC is 1 over j omega C. Capacitor impedance is inversely proportional to the frequency. The faster the frequency changes, the lower is the impedance for a capacitor. And hence 1 over j 2 pi fc. So ZC is going to be 1 over j omega c is equal to 1 over j 2 pi fc. From here, if you notice, actually, let's not do that. That was colon. XL is simply 2 pi FL without the J. And XC is 1 over 2 pi FC. Okay, right? ZC is 1 over J omega C. XC is 1 over omega C, or 1 over 2 pi F times C. And XL is 2 pi FL. This J, what is 1 over J? What is 1 over J? Anyone?
Negative J.
Negative J. And there's a quick derivation about it. I typically like to do it because, again, this is supposed to be knowledge for all, all engineers. So if you have 1 over J, you can represent this as 1 over J times J over J, or I, the imaginary number. So this gives you J over J square. Is J over minus 1, hence minus J. So ZC, which we write as 1 over J omega C, becomes minus J 1 over omega C, or minus JXC. And so this is rectangular coordinates, right? If it's J, the imaginary number, then it's rectangular coordinates. In polar coordinates, it's simply written as omega L with a phase angle of plus 90. And this is 1 over omega C with a phase angle of minus 90. So depending on what equations you need in your problem, you can write either the rectangular coordinates or you can write the polar coordinates directly. What I typically tend to do is, if I find, I determine both coordinates at the same time. Both at the same time. Because later on in the problem, I never know which ones I need. So I find both the rectangular as well as the polar coordinates at the same time. Okay, let's take a pause. There's a lot of information, so think over it. Let me know if you have any questions.
Professor?
Yes.
When we're doing the actual the sine or the cosine equation, do we have to convert the phase angle to radians first because omega is in radians?
No, we keep the phase separate, especially because we are specifically because we are representing it as a vector, and for that vector we need a phase angle. We don't need omega because omega is angular velocity, and it has absolutely no meaning when we are trying to describe the vector. So we keep it separate. Yeah, so if an expression is given to you as like sine omega t plus 50, then it would simply become cos of omega t plus 50 minus 90. And the phase angle would become minus 40. So it will be cos omega t minus 40. Does that make sense?
Yeah, that makes sense. Thank
Okay,
you.
all right. Okay, any other questions? Oh. So impedance, one final thing, impedance is a complex quantity. When you plot the vector in a complex plane, the projection of that vector on the real and imaginary axis gives you the real part, which is the resistance, and the imaginary part, which is the reactance. Three sides of a right angle triangle, and we get what is known as the impedance triangle. Impedance triangle. And the phase angle, theta, is basically the difference of phase between the voltage and the current, right? Impedance is V over I, meaning theta V minus theta I. So this impedance angle theta is theta V minus theta I. This is again going to be important when we study AC power next week. Okay, we'll study AC power next week. In AC power, you have power triangle, which will be exactly, well, not exactly the same, but it'll be very similar to this because it is a complex quantity. And the phase angle is known as the power angle. That power angle is again theta V minus theta I. So again, impedance triangle is basically describing the three sides of the right angle triangle comprised of the impedance, resistance, and reactance. The phase of the impedance is the phase difference between the voltage and current for that specific component. Okay. So an ideal inductor, R is 0, right? So it's only X. So X is right here on the Y-axis, a real imaginary, the positive imaginary axis. For a capacitor, R is 0, but angle is minus 90. So it is pointing straight down. So if you were to plot ZL, ZL would be pointing up at 0, 0, right? Because R is 0, so it's pointing up. Whereas ZC is minus 90, so it's pointing down. Minus 90 plus 90, right? Minus is, so if this is 0, this is plus, vector rotates counterclockwise, and vector rotates clockwise, then the angle is negative, minus 90. So capacitor impedance, minus 90 is pointing straight down, inductor impedance pointing straight up. This concept is again going to be very important when you get to AC power. We'll learn about AC power for inductor and capacitor. Inductor AC power is going to be positive, pointing up. Capacitor power is going to be pointing down. And that's the reason why. All right, questions? Any questions at all? You're thinking something. Yeah. Phase angles. It's, again, as I said, it's a lot of information to take in. So if there are no more questions, or no questions for now at least, let's move on. Okay, so all the fundamental laws that we learned about, Ohm's law, KVL, KCL, they still work for AC circuits. Okay, they still work for AC circuits. There's no other change to those. Note that all of the notations are now in uppercase because we're indicating a vector. Okay, so Ohm's law works for all three components. KVL works for all circuits. KCL works for all circuits. You can apply all of those techniques exactly the way we learned them. The only difference is each quantity is now a vector. So we have to take the magnitude as well as the phase angle into account when we perform our math. So for instance, in the lab, if you perform an experiment and you measured the voltage, so how many of you are taking the lab? Okay, just almost all of you. So if you measured the voltage across each one of those components, R, L, and C, and you added up those magnitudes or those values, they would not satisfy KVL, as you learned in lab 6. And the reason it doesn't is because it's a vector quantity. When you measure, you're only measuring the magnitude. You don't have any information about the phase angle. And if you don't have information about the phase angle, then your KVL will not work. hence the phasor diagrams. The phasor diagrams allow us to find the phase angles. Okay, impedances in series and parallel. One thing I glossed over was the symbol for an impedance is the same as for a resistance. So reactance, resistance, and impedance, they have the same symbols and the same units. And so impedance in series and parallel add up the exact same way that we add up resistors. Same as resistors. Again, remember I said we're going to use the exact same analysis techniques that we learned about previously. So they add up the same way as resistors. Important to keep in mind, if you have two or more inductors in series or parallel, you can add them together and combine it as one single inductance, right? You can convert the inductor into its impedance and add up those impedances also. For capacitors, when you have capacitors in series, they add up the opposite of resistors. But if you take the impedance of those capacitors, they would add up exactly the same way as you were adding up resistors. Okay, so there's another potential point of error where students sometimes make a mistake. And you can also combine impedances together, meaning you can combine a resistor, a capacitor, and an inductor impedance together. You cannot combine a resistor, inductor, and capacitor value by itself, but if you have the impedance, then impedance is basically the same quantity, so you can combine those together. Mathematically, of course, resistor will be real, inductor and capacitor would be imaginary. But you can combine those impedances together. And then there are reciprocals. So this is something, again, we won't solve any problems using these, but this is something, these are some quantities that you should be aware of. Someone talks about conductance. Conductance is one of the first things we learned about in this chapter or in physics, right? Electrons move through a wire conductor. It allows the passage, it's known as conductor. So it's that quantity is termed as conductance. Opposition to the passage of electrons is resistance. Similarly, so basically, excuse me. So conductance is the reciprocal of resistance and vice versa. But similar to that, we have the reciprocals for reactance and impedance. And those reciprocals are admittance and susceptance, respectively. And here we note the uppercase notations for all quantities. So Z is simply 1 over Y, R is simply 1 over G, X is simply 1 over B. Symbol for all three, impedance, reactance, and resistance, is ohms. Symbol for conductance is Siemens. And so it is the same for admittance and susceptance. And the reason we study these in electrical engineering is because when you have lots of components in parallel, it is easier to analyze them by using the reciprocals. As a quick example, if you have multiple impedances or multiple, let's say, capacitor, resistor, inductor in parallel, you're trying to find ZEQ here. If you simply find Z1, Z2, and Z3, you have to take the reciprocal of the impedances, then you add up and you take the total reciprocal. But if you already have the reciprocals separately, meaning if you're already describing if you already describe B as 1 over X and Z as 1 over Y as 1 over Z, then all you'd have to do is simply add up all the admittances, Y1 plus Y2 plus Y3. Your equation solving becomes easier. Applying voltage division, current division becomes easier. So current division becomes extremely easy when you work with reciprocals like Y, B, and G. Okay. So again, I won't make you solve problems using any of these equations, but it's something that you should be familiar with. So anytime someone talks about any of these quantities, you should be able to understand what they're talking about. Okay, questions? Any questions at all? Again, as I said, last class and this class, lots of concepts. Main thing to understand is that we will use the exact same analysis techniques that we learned about in chapters 1 and 2, except now we are working with complex numbers. So let's look at a few examples. Okay. There's 5 examples in there. We'll build it up step by step. The first one simply asks you to find the value for Vs of t. Vs of t has 2 components, 10 cos omega t plus 10 sine omega t. Okay. Both are being summed up. Now, whether it's a addition or a subtraction does not matter, right? Whether it's an addition or subtraction does not matter. And I just realized I left my notes in the office. Let me see if I can pull them up here. Let me go over the process and then we'll talk about the math later separately. So example 1. Example 1. Vs of t. So when you're faced a problem like this, it does not state, but it is assumed that you should use phasor techniques. Okay, you should use phasor techniques to perform this operation. So if I want to write the phasor, what do I need? I need the expression to be in cosine form, right? I need the expression to be in cosine form, which one of them is already in cosine form. So this remains 10 cos omega t. This becomes 10 cos omega t minus 90. Now, one of the first things that you have to remember is that if you want to add or subtract 2 signals together, the frequencies must be the same. If the frequencies are not the same, you cannot add or subtract them. You simply leave them as it is. You cannot do anything about those. You cannot add or subtract those frequencies. Okay, there's also the principle for noise cancellation. Noise cancellation technology, you will have a microphone, it'll pick up the surrounding conversation, surrounding signals, and inverts the phase by 180 degrees. Then it adds it to that same noise signal that you want to exclude. Meaning the frequency is exactly the same, but the phase is now different. So the phase is now different. You add plus 180 or minus 180 to the same signal, it cancels out. Vector math. That's noise cancellation technology. Where the frequency is not the same, you would keep hearing all of those noises and sounds. So Vs of t is 10 cos omega t plus 10 cos omega t minus 90. You write the phasor directly. Actually, this should change. This is going to be my notation for phasor for V. It's easier to actually recognize it in print rather than writing it out. So phasor for this would be 10 angle 0 plus 10 with a phase angle of minus 90. Now you're adding up 2 vector quantities and both are in polar coordinates. You can program it directly into your calculator and perform this calculation. My calculator cannot do this. So I have to convert this 10 angle 0 into a rectangular quantity. Okay, 10 angle 0 into a rectangular quantity. I don't have my notes with me, but 10 angle 0 should, if the angle is 0, it should lie on the x-axis, right? Lie on the x-axis with the length of 10. So the rectangular quantity for this would be 10 plus j0. Someone perform this equation or calculate this on your own device, please, and let me know if my answer is going to be correct. And 10 with the angle of minus 90 would be pointing straight down, minus 90, right? And this is 10. So this would become real part is 0 and imaginary part is minus j10. So Vs becomes, I add the real parts together, so it's 10 plus 0, and the imaginary parts together is 10 minus j10. And 10 minus j10, rectangular coordinates, let's see. So this quantity would become 10 right here and 10 over here. So my vector is somewhere here with minus 45. What is the length of this one? 10 square plus 10 square, 100 plus 100. So square root of 200. What's the square root of 200? I have no idea without using a calculator. 1.14. So 14 point. No, not 14 point. 14.14. Yeah, 14.14. With an angle of minus 45. That would be the answer. If you have a programmable calculator, you can go directly from this step to here. Okay, programmable calculator, you can go directly go from this step to final right there. But you need to be an expert at using your own device. Because if you make an error going from this equation, your setup to your final answer, and you forget to input it correctly, instead of a minus 90, you might put in a plus 90, your entire solution is going to be incorrect because your entire grid is now based on this. If you show the intermediate steps in there, I might be able to give you partial credit. But if you just have one equation and then the final answer, which is incorrect, there is nothing on paper for me to give you credit for. So be very, very careful. That's why I said on the announcement, in the email, and also in that practice sheet, you should practice it. It is not just for this class. As engineers, you should be an expert at using complex numbers. Okay, so you can program this in there, come up with this answer. Now, if the answer asks you to find Vs of t or I of t, it is asking you to find the answer as a function of time. If it is a function of time, you cannot leave the answer in phasor form. You have to perform the inverse phasor transform and write out the expression in the time domain. It is not, I mean, it's rather straightforward. So Vs of t would simply be 14.14. The inverse phasor transform would be a cosine, again, a right angle triangle, so it'll be a cosine. The frequency does not change. So the original frequency is omega. You would simply write omega t and the phase angle minus 45. And the units for the entire overall expression is volts. Okay, volts. So 14.14 cos of omega t minus 45 degrees. That would be your final answer. Actually, already at 10:02. So let me end class here today. What I wanted to do was also cover the next two examples. What I might do is I might create a short video and post it online solving examples 2, 3, 4, 5. Quiz on Monday based on the material that we have learned in this chapter, so chapter 5, AC analysis. I will provide the details sometime later today. But again, for now, quiz 6 will be this coming Monday. All right, and we'll tackle AC power right after that. So have a good weekend. Let me know if you need to see me. I'll be in my office today, or I'll be available over Zoom. If you need to see me over Zoom, you send me an email, please. Do not just wait in the waiting room. Okay, send me an email and I will log on when when you find a convenient time for both of us. All right, have a good weekend and I will see you all Monday.
Thank you, Professor.
Yes.